equation for impedance. We have seen it for impedance under what is called semi-infinite boundary conditions. Okay. So, just to refresh your memory, we have taken the fixed second law equation with the appropriate boundary conditions. We had derived the equation for steady state current values at different rotational speed and as a function of DC potential. We have also derived the equation for impedance assuming that the boundary condition is at delta equal to infinity, that semi infinite boundary condition. Okay. So, we saw that you can write it in the Faradaic impedance in 3 different terms. One corresponds to charge transfer resistance, another corresponds to Warburg impedance for species A, another for species B, and under certain conditions, that if we say DC potential is 0, you can simplify this and split it into these 3 components such that the charge transfer resistance does not have any diffusion term and the diffusion resistance does not have any kinetic term. And of course, if you have semi infinite boundary condition, only EDC equal to 0 is the steady state condition. You will not get steady state condition for any non-zero value of EDC. And we have seen that the complex plane plot would look like the one that is shown here. That is a 45-degree line with an offset of course to the origin, and you have the body plot represented here for certain values of kinetic parameters and diffusivities. So, what we want to do is to derive the equations for a finite boundary condition. That means that boundary layer thickness is finite. So, the equation is going to be the same, basic equation is going to be the same. The solution, general solution is also going to be the same. We are going to apply a different boundary condition. Previously, we would have said at x tending to infinity, this is the result, whereas here we are going to say x equal to delta, it is going to be like this. So, the general solution, okay, it is going to be in Ca tilde and Cb tilde, and again to refresh your memory, CaAc was written as CaAc0 e power j omega t plus phi a, and then we wrote it as Ca tilde e power j omega t. That is to say, Ca tilde is defined like this, and similarly we have Cb tilde, and our original equations were and likewise in dou Cb by dou t. Then we said Ca can be split as Ca dc plus Ca ac, and therefore, these equations we wrote in terms of Ca ac. And then we said Ca ac can be written in this form, that is our assumption, and with that assumption this PDE became ODE. That means, we have a form for this, therefore, we are supposed to find how CAC depends on x. Then this became equation in Ca tilde, and that is how we got these solutions. Okay. Now, we want to say at x equal to 0 the boundary condition is the same, that is the flux of this A species tells us how much current is coming through it, how much Faraday current is there, and that is also related to the flux of the species B. Just the sign is opposite because A comes in, it gets converted to B, therefore, B goes out at the anodic potential. Okay. Second boundary condition, instead of saying x equal to infinity, we say x equal to delta, concentration is Ca bulk and Cb bulk, which means if this is the electrode, this is the boundary layer, beyond this concentration remains the same. Here when I apply only DC potential, it is possible this is Cb and this is Ca, a straight line, linear line, and if I apply a sinusoidal potential on top of this, concentration here will fluctuate with time, concentration here will also fluctuate with time, concentration here will fluctuate, here also it will fluctuate, and you can imagine that amplitude of fluctuation will go down as you go further towards the boundary. And at the boundary we say it is not changing, Ca is Ca bulk, Cb is Cb bulk, which means Ca tilde is going to be 0, Cb tilde is going to be 0, that is because the AC component magnitude is 0, only the DC component remains there. So, let us put this, we are going to solve it for Ca, and then I am going to say if you solve for Cb you are going to get similar thing except with the negative sign. So, we want to calculate A1, A2 using these two boundary conditions. Can you try this? Earlier case, when x equal to infinity, we could say A1 has to be 0 because otherwise it goes to infinity. Here you will have to solve these equations by solving them simultaneously. So, we take this equation, we take this boundary condition and the second boundary condition, which is written as Ca tilde equal to 0 when x equal to delta, and then use this to find value of A1 and A2. Okay. At x equal to delta, concentration is constant, it is Ca bulk, that means fluctuations are 0, which means the amplitude of the concentration oscillation is 0. It will take you few minutes, but it is not that difficult. First part, you can show that A2 is related to A1 with a factor of e power 2 square root of j omega by dA delta. Right, you can rearrange the first equation and write A2 in terms of A1. Second is little more complex, but we have seen the procedure. At x equal to 0, this is what we know. This means when I write in terms of tilde, Ca tilde, I can write in terms of AC plus DC. So, I would get Ca AC dou by dou x diffusivity equal to IF AC, and that is the same as del IF. That is one way of writing. Another way of writing it is IAC 0 e power j omega t plus phi I. Another way of writing it is IAC tilde e power j omega t. So, out here I would write it as Ca tilde e power j omega t. That means I should write dou Ca by dou x, dou Ca tilde by dou x at x equal to 0 is same as IF by diffusivity of A and F Faraday constant, IF tilde on the numerator. So, instead of writing like this, I can of course bring this dA below to the denominator here. Instead of writing dou Ca by dou x at x equal to 0 equal to IF by dAF, I can write dou Ca tilde by dou x at x equal to 0 is IF tilde by FdA. And of course, I can take the derivative of Ca with respect to x, and then at x equal to 0 I can find the value. Now, using this equation and this equation, I can write A1 and A2 in terms of known parameters. Up to this, are you okay? I would actually like you to try that and get this. A lot of times in the books you would see that this is the equation, but how do you get it? And when you derive, you would also see in what conditions they are valid. So, for example, you should not take the equation for semi-infinite boundary condition and apply it when EDC is not 0. If you are going to use a DC offset, DC bias, you should always take, at least if you are going to compare with analytical solution, take the finite boundary layer condition. In case the boundary layer thickness is large, you estimate it to be large, use that large value, and when boundary layer thickness is large, that finite boundary layer thickness equation should approach the semi infinite boundary layer thickness equation. That is okay, but you should be aware of what are the limitations of the formula that we derived. So, if you get the value of A1 and A2, do you get an equation like this? So, concentration fluctuation, the magnitude and phase depend on the location x. We really want to know the concentration fluctuation at x equal to 0, but here you can see if x equal to delta, you get 0 fluctuation. So, the equation at least appears to be okay. When x equal to delta, you will get e power 0 minus e power 0, therefore, the numerator goes to 0, fluctuations go to 0. At x equal to 0, fluctuations are maximum. This is basically substituting for A1 and A2. So, I have skipped one or two minor rearrangements here, maybe I should not. What is the value of A1? IF tilde by, okay. We got this before, and A2 is going to be minus A1 correct. We got this from the first boundary condition, and therefore, it is going to be minus IF. If I multiply by e power 2 square root of j omega by dA, I am going to get correct. So, A2 is going to look like this. A1 I can write like this, or I can write in the numerator as now A1 multiplied by e power square root of j omega by dA x is going to give me e power j omega by dA square root x minus delta. So, this first part comes from the A1 component. Okay. This minus sign comes here, denominator remains the same. A2 is going to be e power j omega by dA delta minus x. Instead of writing it as delta minus x, I write it as minus of x minus delta, so that it can be written in a little more compact form. This numerator is actually 2 times hyperbolic sine, it is written as sin h, and the denominator is 2 times hyperbolic cosine. So, the factor of 2 cancel out. So, I would get if tilde sin h, the numerator has delta minus x, denominator has cosine h with the delta factor, and then of course, you have 1 by j omega dA for the concentration of A. So, it needs careful algebraic rearrangements, but that is enough. And C A tilde similarly C B tilde is going to be same as that, except instead of the diffusivity of A, you would have diffusivity of B involved in it. Instead of plus sign, you will have minus sign there, because the boundary conditions, the second boundary condition is the same. At delta x equal to delta, you will have C B fluctuations at 0. First boundary condition, it would say IF by F is minus of dB dou C B by dou x. So, because of that, the factors will have interchanged in the sign. So, it will look similar to C A tilde, but with a negative sign, or the negative sign is gone here. and instead of dA you will have diffusivity dB there.
But sir, at x is equal to delta, we got both Ca and Cb equal to 0.
Yeah.
But at some boundary, there must be some one component exists.
I'm sorry?
We
We don't get Ca and Cb to be 0, we get fluctuations in Ca. Ca tilde and Cb tilde to be 0. Ca is actually Ca bulk, Cb is Cb bulk.
Sir, can you go to the previous slide?
Sure.
Boundary condition.
Yes.
So here we are solving that dou Ca tilde by dou x, right? At x equal to 0.
Yes.
So if you substitute A2 as A1 in the form of A1 in that, we will get IF tilde by dA into F, right? To solve A1 from that equation, that square equation, dou Ca tilde by dou x
Yeah.
at x equal to 0.
Yeah.
From that equation, if we substitute A2 in terms of A1 and solve for A1, right?
Yeah.
In that case, IF tilde by dA into F we will get, right?
IF tilde by d into F, yeah.
Divided by some root j omega dA into 1 plus something will get.
We are okay with this equation?
Yeah, that okay.
Okay. Now look at this, I am still keeping it, this is there. Now if I want to find the value of A2 or A1, what do? I take this equation and substitute it here. What would I get? I am going to write square root of j omega by dA A1, okay, minus, write it a little more neatly, this is correct, because instead of minus A2 I would write it as A1 e power 2 square root of j omega by dA delta, okay. That is equal to IF tilde by dA F. Now I can pull A1 out of this, so it is going to look like A1 equal to, right side I will keep it as IF tilde by dA F, I divide by j omega by dA, okay, I have missed the dA, have I? Okay. And then instead of writing it as 1 plus e power, that is one way of writing it. Another way is to pull out, I can multiply and divide by delta, and then I will get yes, I have missed the F factor is there, I have missed the dA, yeah, correct. That is one way, or I can write it as, I can bring it in and then cancel, yeah. Right now it is easier to write like this, and that means it is correct.
So can we say that Ca plus Cp will be Ct always? Can we consider a function like overall function will not change? So instead of
No, not overall function, overall concentration at a given location, not exactly, not always. If dA equal to dB you can do that.
But according to this equation, for 1 mole we are getting 1 mole of B. This is a
1 mole of A will get 1 mole of B. Okay, if you take the entire volume on the boundary layer, you can say that, but not at one location, because concentration of A can build up or B can build up, because B may not diffuse that fast. Concentration of A may decrease up to some level. So when a concentration of diffusivity of A and B are equal, A will get consumed, concentration will go down, it will not go to 0 because it is coming at a particular rate. Okay, let us take only steady state condition. Concentration of B will also build up, but if B diffusivity is slow, it will build up more. Net 1 mole of A will give you 1 mole of B, there is no doubt about that, but the concentration of A plus B need not be a constant, regardless of any, irrespective of the location and space, you can't always say that.
But for a binary system, we say that DAB is equal to DBA. That's what we have proved in mass transfer. If we have a binary system,
Yeah.
diffusivity of A in B.
Yeah, here it's mixture. You are talking about two gases. So, it is just diffusivity of A in this mixture, diffusivity of B in this mixture. And if we take for example, ferro-ferry example, they will not be the same. In fact, it is more or less diffusivity of A in water and B in water, although it is a mixture. Yeah,
Then it will be different. I mean,
it is different.
but if we have two mixtures, we have a binary mixture. Here we have A and B, and we don't have any other substance. In that case, we
Even here, sometimes people will approximate and say dA is roughly equal to dB and simplify. It makes it little easier to look at this equation because it will have fewer terms.
But for binary system, we have proved that JA is equal to minus JB.
Yeah, here also.
Here also.
Yeah,
So if dCA by dx is decreasing, in that case, even if we consider that dA is not equal to dB.
Yeah.
So if one is increasing, the other component of that is decreasing.
decreasing, yes. That is why we write the boundary condition as, when it is positive here, it is negative there. The flux we do consider it as the amount of A that is coming in is going to be equal to amount of B that is going out. J of A and J of B with the opposite sign, they are equal. But unless dA and dB are equal, you can't say the CA and CB, the sum of them is going to be the same.
But if it will not happen, then at one point the overall composition will keep changing.
It won't keep changing, it will be a higher value, but under steady state condition, that higher concentration gradient with lower diffusivity is allowing it to go at the steady rate. Amount of A that is coming in should be equal to amount of B that is going out. Okay. So, if diffusivity of A is much larger than diffusivity of B, that means B diffuses slowly. Okay. Now, a small concentration gradient will allow A to come at a particular rate. Same rate if B has to go, it needs a larger concentration gradient. So, concentration of B will be higher. A would have gone down, for example, initially A is at 5 millimolar, B is also at 5 millimolar. A would have gone down to 4 millimolar because of reaction, it is consumed. B will not be at 6 millimolar, it may need to be at 7 millimolar to go at the same rate. So, under steady state condition, it will build up to a different value, but it will not keep increasing, because the diffusivity is, for example, in this case we assumed it is less or smaller. So, when you apply sinusoidal also, A will come at a particular rate or fluctuate at a particular rate, B will fluctuate at a different rate and it will fluctuate around a different mean value, but it will still be sinusoidal with a different amplitude. You can't assume that the amplitude of A and B will be the same. Based on the diffusivity values, the amplitude values will change, phase value will also change. But if diffusivities happen to be equal, then they can say their fluctuations will be mirroring each other exactly. Here the sign is changing. So, when C increases, A will decrease, that is expected. Amplitude will be comparable because typically dA and dB are in similar range, but you can't assume that they are going to be equal. Okay, now we go back to the original equation, where we write current fluctuation as a function of change in potential, change in concentration of A and concentration of B, and this we have written it as Cb tilde e power j omega t, likewise Ca tilde e power j omega t for del Ca, and now we have written it in terms of If tilde. So, what would happen is dou I by dou Ca, dou I by dou Cb, we have the values, and this is based on the equation I equal to Faraday current is equal to the net rate of production of electrons. I am sorry, it's e power So, from this we saw that IF can be written as IF DC plus IF AC, and IF AC can be written as dou I by dou E. When you take the dou I by dou E, you get F B 1 K 1 DC C at x equal to 0, B minus 1 K minus 1 DC, because when we take the partial derivative we assume concentration of A and B are fixed. Here we assume concentration of B and the potential are fixed, potential is fixed, concentration of A is fixed. You get 3 terms. We got expression for this, this is of course EAC, we got expression for this, got this, and now we derived the expression for del Ca. So, del Ca is basically going to be Ca tilde e power j omega t, and del Ca at x equal to 0, we substitute x equal to 0 there, and you would get sin h by cos h, which is going to give you hyperbolic tangent, and I am also adding the missed diffusivity dA. Previously it was delta minus x, but since we substitute for x as 0, we would get this simplified expression, and if it is del Ca, I should write e power j omega t. If it is just Ca tilde, I will leave the e power j omega t out. Now, if you substitute the entire thing, so I will go and double check whether I need to put the dA or whether I missed it. I think I need to put the dA, but I will just double check. We can write for the first expression, it is easy, it comes in terms of EAC, second comes in terms of IF tilde and e power j omega t, IF tilde and e power j omega t, which is basically del IF. So, we can rearrange and get an expression for IF AC by EF AC, and I am going to delete this so that I can show you that. So, you can see that, right, this is going to give you 1 plus whatever is here plus whatever is here. Here you got a negative sign because it is going to be minus f k minus 1 dc for the partial derivative with respect to Cb. Here you got a negative sign because Ca tilde is with a negative sign. So, when you bring them to the left side, this will also become positive, this will also become positive. So, you would get IF tilde or IF AC 1 plus tan h something plus tan h something, and that is going to be equal to a factor multiplied by EAC. So, you can rearrange and get IFAC by EAC or EAC by IFAC. It is a fairly large expression, but I think you can dA and dB, yes, that is correct, it has to be there. You can invert it and write this in 3 terms again as RT Z omega Z W A Z W B. Sometimes it is written as BW to say bounded Warburg impedance. Sometimes it is called a transmittive boundary condition to say that there is a film, diffusion occurs there, and at the end of this A can come in or go out, B can come in or go out, it transmits. Sometimes they would derive the expression for the impedance in a film where at the end of the film nothing moves in or out. Okay, that would be called as blocked boundary condition. There you would say the derivative of this concentration is going to be 0, because the flux is going to be 0, that means the dCA by dx, dCB by dx at the boundary is going to be 0. So, you may have a film, material may diffuse in and out, but in and out on the diffuse in the sense it may be produced or consumed in this boundary and it can diffuse in and out, but at the other boundary it is not taken. So, it will have a slightly different expression of course, and the way it looks will be different, but the equations are going to be same, except when you finally get the value of A1 and A2 you need to use a slightly different boundary condition. So, compared to that this will be called as transmittive boundary condition. Open finite length diffusion. No, different groups would use different acronyms for this, but we normally say it is bounded Warburg or finite Warburg impedance. So, if I invert it I would get it as 3 terms. Thing is, when delta tends to infinity, when I put large value of delta, what happens to tan h? X tends to infinity, this goes out, it is going to go towards 1. X tends to infinity, or here it is delta tending to infinity. Even when delta is not infinity, its omega is relatively large, it is going to look like tan h is going to be 1. So, what you would expect to see is it should look like the Warburg impedance. Okay, maybe this is not nice, but look like a 45-degree line with offset at this frequency range. Later it is actually going to come down and settle. At limit delta tends to infinity, it is going to look like what you have seen before. Of course, here too, right. So far we have not assumed that the DC potential is 0 in this example. When delta is finite value, when omega becomes 0, what do we see? You are going to get tan h square root of j omega dB dA does not matter. So, it is going to look like 0 by 0, and you can apply L'Hopital rule and get a expression for this. It will settle at a finite value. Right, sin h of x is going to be x, this is going to be 1 plus or minus x square, etc. So, if you do this you would get 1 here for tan x, tan hs hx by x, but then you have other factors. So, when you take this you would find it will come to a finite value, which means this will settle on the real axis. It is not going to be a complex number, it is going to be a real number, and it is not 0. So, it is going to be RT plus some value. So, this is the RT value. At high frequency it is going to look like the 45-degree line, because it is similar to that. At low frequencies it is going to settle here, and that settling function is given by tan h of this terms within bracket divided by this terms within bracket.
So, the first loop corresponds to the CDL.
CDL and RT. This is our solution, which is we are taking it as 0. This is going to be RT, and this will not look like a loop, it will look like a 45-degree line I mean it will not look like a semicircle, it will look like a 45-degree line to some level and then 45-degree line with an offset of course, okay. And it may not even come nicely all the way here and go, it may come like this and go here, but it is going to be different from a capacitive loop which you have seen for a one adsorbed intermediate. But in order to clearly see that, we should always plot it in the equal scale. Plot it in non-equal scale, it can stretch and it is not easy for us to see. So, I have taken certain values and just use the formula and predict that impedance for variety of frequencies and plot it for different boundary layer thicknesses. Okay. So, if you look here, it looks like a semicircle not completely touching the real axis of course, and then it looks like a 45-degree line to some level and then it settles at real axis. When you go to high frequencies, you will not see any difference when the boundary layer thickness is varying. When you go to low frequency, you would see a difference. So, here in the inset all the points are overlapping, only at the later stages they are separating out, and you can see this is not a semicircle, right, it is sort of distorted semicircle. It looks like a nice semicircle, or on the right side the arc is neat, on the left side medium frequencies the arc is definitely not a part of a circle. Now, when the boundary layer thickness is large, why do the impedance values go higher or larger? At low enough frequency. So, at high frequency, why does it look similar for all these boundary layer thickness values? Basically, at high frequencies, okay, fluctuation in concentration is not that high. At high frequencies, you have potential varying. Because of it, the concentration on the surface, concentration of A and B will change, but it can't keep up that easily, the diffusion can't keep up that easily. If you give very high change, very high frequency, very fast change, rapid change in the potential, rate constant will still keep up with that, at least that is our assumption. K will keep fluctuating as quickly as the potential fluctuates, but the concentration of A and B will not fluctuate that much. So, the magnitude of the concentration change, C A is at this level, C B is at this level, if I apply DC potential. If I apply very fast AC, it is going to look like this. If I apply a slow frequency, potential changes to the same maximum extent, but it increases slowly and decreases slowly. That means this can also change, concentration fluctuation can change. It means it will go like this. Of course, when B increases, A will decrease, but it can keep up. So, when I go to low enough frequency, as the potential changes, you can almost look at the DC curve and then say from here I very slowly increase the potential to this and slowly decrease the potential to this. I can say this is how the current will also increase and decrease. In fact, in potential dynamic polarization, we go to a potential, measure the current, we go to another potential and measure the current, and practically we end up doing it at a scan rate, slow scan rate, which means we are thinking it is more or less at steady state. So, from this potential dynamic polarization curve, you can estimate how the low frequency impedance will come. This tells if I start at this DC potential and give a sinusoidal potential fluctuating at a very slow rate, low frequency, current will also going to go like this. I am not giving a large sinusoidal potential, I am giving a small 5 millivolt, 10 millivolt amplitude. So, I can estimate the polarization resistance from the potential dynamic polarization curve. I can look at the slope of that curve and I will get a value. Experimentally, when you compare the polarization resistance from the impedance data and from the potential dynamic polarization curve, you should get within the experimental area, you should get same value. Of course, here it is going to be the inverse of this, because what you get is d I by d E and polarization resistance is d E by d I. So, get the slope, take the inverse of it and then compare with the, here it is going to be ohm centimeter square, here of course, this means it is going to be amp per centimeter square. Do not take the raw data of amp. Other than that precaution, you should get more or less same value.
The polarization resistance is just the impedance, or are you talking about the settling value?
Polarization resistance is the, if you look at this impedance data, it is the impedance at the low frequency limit, which is basically we expect it to be 0 frequency limit, but whatever low frequency you can get. If you get somewhere here, you should extrapolate and get it. It should be a real value and phase should be 0. So, here if I give more and more frequencies, that means lower and lower frequencies, it is not going to go like this, it is just going to settle here. Points are packed more and more closely here. And of course, because I have the equation, I can substitute there omega equal to 0 and find the value. But in general, if you are measuring in experimentally and then you are finding it settling there, you would take that as the polarization resistance. That is one way of experimentally measuring it. Another way is to measure this around this value, go at a, actually you do not have to even go, you go here, settle there, measure the DC current. Then go to another point, wait for sufficient time, measure the DC current, go to another point, wait for sufficient time, measure the DC current. That is one way of doing it, or go at a very slow rate and measure the DC current. Find the slope of that, fit it to a straight line. If it is a curved line, you should fit it to a quadratic equation and find the slope of it. That inverse of that slope would give you a polarization resistance. Basically, it tells if I want to change the potential by a little bit, what is the resistance offered by the system. If the current is large, you can change the potential a little bit, the change in current is large, you have a low polarization resistance. If it does not change that much, you have a large current, does not change that much, you have large polarization resistance. That is to say, I have certain charge here in the interface, I have certain potential, I have certain charge. How easy or difficult is it for me to change it, change the, if it is at 0, it is a change of polarity, you can also measure it at any DC bias. Current is very low, resistance is very high. Now, if I have a large delta versus small delta, if I have a large delta, it is harder for the diffusion. Large delta is one assumption, I mean one way of looking at it. Low dA, diffusivity, dA and dB, that is also going to be equivalent. Okay. So, instead of doing this, of course, this is practically easier to say I have one system, I will change the rotational speed, I will change the delta. You can compare different systems with different diffusivities and you will get similar result. Lower diffusivity will end up giving you larger polarization resistance. But out here I am just comparing different delta values, different boundary layer thicknesses, you will end up getting larger boundary layer, larger polarization resistance. And of course, you can visualize when delta becomes infinity, it is going to look like this and settle at infinity, which is basically a 45-degree line. We are not really going to see where it settles, but you can visualize that as you increase the delta, it is going to approach more and more a 45-degree line for a large number of frequencies before it comes down and settles. And if I really look at the Bode plot, there is a small maximum here, it is not easy to see in this scale, and then imaginary part goes through a maximum here and then another maximum, correct. Real part of course goes, settles, goes and settles again, that means it increases, settles again. Magnitude and phase, of course, here you do not see it, it is starting at 90 degree because it starts like a vertical line. Practical cases, when you have a solution resistance, it will actually start at 0, it will go up in the phase, come down, go up and come down, but it is not a clean symmetric peak because it is not really a semicircle. Okay. But this is a signature that you would see in Bode plot. I think I will continue tomorrow with one more part of it, that is effect of DC potential, and then we will move on to a phenomena called CPE, constant phase element. Okay. We will stop here today. So, we will just continue with where we left yesterday, which is to wrap up the part on mass transfer effects on the impedance, okay, and then we will start with what is known as constant phase element. If time permits, we will also go to the porous electron. So, we were looking at the electron transfer reaction A going to B, and we got a complex expression for impedance. We can simplify this to a more familiar expression if you assume that DC potential is 0, that is at OCP. Okay. So, right now the way I have written is valid for any DC potential with or without DC bias, that is valid, and if we say that the DC potential is at 0, okay, many times people use this for corrosion experiments or other experiments at OCP, in which case you could get a simpler expression where charge transfer resistance will come only in terms of kinetic parameters. The Warburg impedance or bounded Warburg impedance will come only in terms of the diffusion parameters. Okay. But that is not in general going to be true or correct. So, we have seen example where different delta values affect the impedance, especially at the lower frequency. Okay. So, what I want to show you is if you use this expression and calculate for a given delta value, for a given mass transfer limitation, okay, for a given delta value of boundary layer thickness, if we change the DC potential, here the red color rounds circles are the DC potential at 0, the green squares correspond to the impedance when DC potential is 50 millivolts, and the triangles correspond to the case where DC potential is 100 millivolts. So, notice the following: when DC potential is 0, the first loop, which is shown in the insert here, comes, dips down, and then it starts to increase and then comes and touches the real axis. This corresponds to charge transfer resistance, and this value corresponds to polarization resistance. This value meaning we are assuming, of course, solution resistance is 0. Okay. Earlier, for a reaction like this, if you assume that mass transfer is not a limiting factor, if you assume that it is very rapid mass transfer, at DC potential of 0, you might get a spectrum like this in the complex plane. When you increase the DC potential, it is going to go down 100 millivolts, 150 millivolts. The charge transfer resistance and polarization resistance both were the same in that case, because you would represent that by just one resistance, in which case polarization resistance, charge transfer resistance, they are the same, and both of them decrease with respect to potential. We also saw other examples where is A going to B, B going to C. We would have used a slightly different notation. We might have said metal going to metal plus adsorbed plus electron, metal plus adsorbed going to metal 2 plus solution plus electron. This is one example. Those cases, generally charge transfer resistance tended to decrease with increase in potential. However, when you have mass transfer limitation, when you increase the potential, the charge transfer resistance actually increases. So, if you look here, the red circle will tend to touch the real axis earlier, green will probably touch somewhere here, black, if it were extrapolated and touching it, it is going to touch here. This of course corresponds to the ZW or ZBW, BWA, BWB for both A and B species bounded Warburg impedance. Right. Now, why does it behave that way? When you increase the potential, we expect the reaction to happen at a faster rate. At least one of the reactions should happen at a faster rate. Okay. Faster rate means more electron transfer, and we would say less resistance. So, if you go back to the expression, the red color part in the numerator with the black color part in the denominator corresponds to R t. When I change the potential, when I increase the potential, K 1 d c will increase, K minus 1 d c will decrease, concentration of B will increase because I am producing more B. When I increase the potential, I am producing more B, I am driving the forward reaction more, concentration of A will decrease. Earlier, when we assumed mass transfer was very rapid, we said C A is fixed, C B is fixed. Okay. Then when I increase the potential, K 1 d c will increase, K minus 1 d c will decrease. In general, the denominator will increase, and therefore, we would say the charge transfer resistance would decrease. Now, although the effect on K 1 and K minus 1, the effect of change in potential on K 1 K minus 1, they are the same, but concentration of A will decrease and concentration of B will increase, and that has the effect, that net effect is that R t is larger, that means denominator is a smaller number. So, whatever learning we had, that pattern recognition that okay, increase the potential, it decreases, that is valid only when the mass transfer is very rapid. When mass transfer plays a role, you can't extrapolate whatever you have learnt there and use that here. Okay. Same with polarization resistance, we get a larger polarization resistance when the DC bias is changed. When it is 0 DC bias, you get minimum resistance for RT and RP. If you go to minus 50 millivolts or minus 100 millivolts, it is going to be similar to this, which means if this is 0 resistance, 50 millivolts plus 50 may come here. Of course, diffusivities are, I do not remember what the values I assume there are. If they are the same, minus 50 will also give me the same thing, I cannot differentiate between these two. If they are slightly off, then these numbers will be slightly off. So, when I go to a larger potential or a more negative potential, both cases the impedance will increase, impedance at the mid and low frequencies will increase. High frequency, of course, it is determined by the capacitance value, as long as the capacitance value is assumed to be the same, you will get similar results. Okay. But plus 50 plus 100 will give like this, minus 50 will also go in the same way, plus 50 will show up, minus 100 will also come in the same way, a spectrum for plus 100 millivolts will show up. And when I represent that in a Bode plot, imaginary part, of course, there is a slight increase and decrease and then a significant increase and decrease. Real part is going to be flat at low frequency, meaning it is not changing that much here, it decreases, there is some sort of flat area here and then it decreases again. You may not see it very clearly here, but that is asymptotically going towards it. This again, it is starting at 90 degree, that means it is going vertically up. So, its the phase is at 90, although when you have a resistance, when you have a solution resistance, it will start close to 0 and then it will go to 90, come down. This again shows a second peak corresponding to the mass transfer resistance here.